Thanks. I will begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. For you got our work today. Help us to, again, Lord, just glorify you in whatever we do, Lord. In your name I pray. Amen. Okay, so today, two orders of business. The first is to try to give you a few examples of using the singularity theorem, if you want to call it that. So basically, here's the theorem we have. The solution to y prime prime plus py prime plus qy equals to 0. All right. In the complex sense, will exist on a disk centered at, let's say, z naught, which you could say x naught plus I y naught, up to the nearest singularity. Now, a singularity, let's say, I'll call it z star, all right? So a singularity is going to be a point. What this would mean is that P or Q are not analytic at z star. Now, by and large, let me just sort of tell you the preponderance of our examples. Basically, this means you've got division by 0. Division by 0 at z star is usual troublemaker, all right? So most of the, in fact, probably all the examples I'll look at today, the departure from analyticity is going to be coming from division by 0. All right. Now here's a picture. I'll draw you a picture of what's going on here. Now, so if I'm looking for solutions, and we won't actually do this, but if I was looking at solutions centered at z naught like here, all right, and suppose that I have a singular point, you know, here. Suppose this is a singular point for my differential equation, then this theorem says that, you know, what's going to happen is you're going to get a solution to the differential equation in the complex domain, which will converge, a power series solution, that is, a power series solution which will converge on this disk. I don't know what happens on the edge. That's the way the math works out. But I certainly will get a solution. Solution exists in here, okay? Okay, now, on the other hand, so that's not actually what we do, because this is not a course in complex variables, right? But if we did have such a course, we'd have this theorem, and you could properly develop it. The theorem that I'm bouncing off of is something we might do in math, in the complex analysis class here. Maybe not, depends. But here's the more interesting case. What we're actually interested in is what? We're interested in real solutions, right? So what happens when you choose the center point, the center of your solution, z naught? Let's say it's 0. That's usually what we do. Usually we look for Maclaurin series solutions, essentially, right? We put z naught equals to 0. Well, this theorem then says that if you center your solution at 0, the solution could go out, it could get out this far, right? This would be something like, I can be guaranteed my solution exists in the complex sense on that disk. Now, we don't actually care about all of the points in the complex plane where it converges, right? I mean, that's great, but what do we care about? We care about the real solution, right? But you see that actually is included in here, and in fact can be understood as the restriction to the complex solution. So what you look at is the intersection of this disk in the complex plane with the real axis, and that tells you what your domain will be for the solutions, power series solutions you find to a differential equation. So this is the technique to find how big your solution's domain will be for an ordinary point. So here's the process. To find a domain of solution at ordinary point. An ordinary point is one at which P and Q are analytic. So number one is we identify all singularities in the complex plane, right? And singularities are, again, are points where the coefficient functions P or Q don't have Taylor series, because usually there's division by 0 at those points. That's point number one. Identify the singularities. Point number two is you make a picture. Make a picture to guide your thinking. Plot them. All right? In the process of making that picture, you want to find closest singularities to your chosen center. Let's call that Z0. So we're looking to describe how far away from Z0 the solution will exist. So make a picture. You find the closest singularity to Z0. That determines the radius of convergence, right? So like here, this distance, the distance here would be the radius of convergence. It literally means radius in the complex plane, right? But we still use that terminology in calculus 2 to refer to the radius of convergence, even though, of course, in calculus 2 we're just looking at, line segments. And step 3 is to determine the real interval of convergence, right? So in this class, because I decide, there's really nothing stopping me from making Z0 complex, but I always give you guys Z0 is an element of the reals. Okay. So this is the procedure. Example 1. Let's see here. How about y prime prime plus 1 over x squared plus 1 y prime plus 1 over x squared plus 4x plus 5 y. So to give us a place to start. All right. So my P, this is P, this is Q. Where are the singularities? Now, first of all, neither P nor Q have any real singularities. In fact, both of these are irreducible quadratics. If you look at them, they've got no real solution. So as real functions, P and Q are well behaved everywhere. You pick any real number, you can find a Taylor series which represents P or Q close to that point. All right? But these do have singularities in the complex sense, because P of x, right, is equal to 1 over x plus I times x minus I, right? And q of x is 1 over, well, that's x plus 2 quantity squared, right, plus 1. So that, in fact, can be factored as x plus 2 minus I times x plus 2 plus I. So what are my singular points? And we have singularities at z star, let's say, equal to minus I, and how about these guys? Minus 2 plus I, and this one gives me minus 2 minus I. There are 4 singularities. So at this point, I have, I still haven't chose a, I haven't chose a z naught yet. All right. What I'm going to do is I'm going to look at some different choices of z naught and see how it plays out for us at different choices of z naught. But I'm going through the process. I just haven't fixed a z naught yet. So I've step number 1, I've identified all my singularities. Step number 2, I need to make a picture. All right. So the picture is something like this. So I usually use little x's for my singular points. There's I. Here's minus I. Let's see here. Minus 2 plus I. Where's that? That's like up here. And then minus 2 minus I is it's the other. It's down here somewhere. So there's my singular points, right? Now you guys give me any place to center a solution, and I can tell you how far that solution is going to exist as a power series. You pick any center you like. I'll start. You start me out, Mr. Ron. What's that? 0? Yeah, that's fine. 0. I did say any place. That's true. It's just. So what's the closest singularity to 0? Yeah, they're both distance 1, right? So that means the radius of convergence is 1, and so my solution, I can't draw. That was supposed to be a circle. Oh well, I tried. So that one, so if we choose 0 as our center point, then z naught equals to 0 implies minus 1 to 1 in domain for solution of the form. What's the solution? The sum, I'll get away here in just a second, a and x to the n. Again, so I was given 0 as the center point. You can see from the picture that plus or minus I is the closest one, right? And so what that says is that if I build a solution, a power series solution at this ordinary point 0, which looks like this, then the domain of that will include minus 1 to 1. I'm not sure about the endpoints. You have to check those. That actually would require much more calculation. I'd actually have to plug them in and work it out. It would be pain. Yeah.
Now, if it was at 3, would it be n equals 3, or still start at 0?
Let's see here. If we, yes, next case, I've been given 3 as my next center. That would be over here, right? Roughly speaking. So z naught equals to 3. What would the center be then? I mean, what's the radius of convergence? What's the closest singularity? Yeah, it's still the same 2, but like that, right? So now, to figure out the radius, I actually have something to do, don't I? I need to figure out how far apart those 2 points are. How do I do that? So case number 1. Case number 2, if I put z naught equals to 3, then I plus or minus I closest, right? To find the distance, what I do is I calculate z naught minus the singularity I'm interested in. This is the modulus, the length as a complex, the length of the complex number, right? So the modulus, we're looking at 3 minus I, all right, let's say. And so that's equal to the square root of 9 plus 1. It's the length of the vector. What does it go? It goes 3 over, right? It goes 1 up. It's the length of that vector. So square root of 10 is my radius for that one. It would not be 3. The reason it was 1 here is because I and minus I are 1 unit away from 0. But 3 is not 3 units away from plus or minus I. In fact, it's the square root of 10. That's the distance it is. So from this and the theorem, we learn that solution of form sum over, say, b sub n, x minus 3 to the power n equals 0 to infinity, converges on 3 minus root 10 to 3 plus root 10. Again, I don't know about the endpoints without further calculation. Much further calculation. Where it gets more fun, of course, is if you pick a point where maybe you're not sure which one you're closer to. Now here you'll probably be able to tell me if I pick, for example, what about here, minus 1? I guess that one's obviously the same distance from here to here, isn't it? My picture's not quite right there, but yeah. They're both root 2 away from the singular point, right? Yes?
We're not supposed to do n like every situation, right?
Usually I will do something like, here's a differential equation. What's the domain of where can you be sure the solution exists given your solution has this form?
Oh.
So the way I could ask the question, here's the way I could ask the question 3. Given y equals to the sum c sub n, x minus 1.5, well, plus 1.5 to the n equals 0 to infinity. Where does this solution exist? Now, I should be more careful. I should really say is on what open interval does this solution? See, this right here is an open interval. You guys are supposed to know what this means. When I say interval, it means a set of numbers like that, a to b.
It's easier with z naught.
Say again?
So you will be giving us z naught basically.
Yeah, I can ask the question in other ways. I mean, the point here is to understand the theorem. Yeah, but that would be a common solution problem, a common problem type there. So if I change, minus 1 is boring because it's the same distance between all 4 singularities. But 1.5 minus, so if I have plus 1.5, that means that z naught is equal to minus 1.5, right? And so there, it's fairly clear geometrically that that's closer to minus 2 plus or minus I, right? But it's not at all clear what the radius is from that point to that point, right? I got to figure out this distance, right? But to do that, what I do is I take the modulus of minus 2 plus I minus a minus 1.5. That gives me the length of the vector. In other words, what's the length of the complex number? 0.5 plus I. That's, the square root of 0.5 squared plus 1. That's how long that complex number is. It goes 0.5 units in the x, right? And it goes 1 unit up. So that's the square root of, I guess it's the square root of 1.25, huh? So the answer to my 3 would be, you can be certain on minus 1.5 minus the square root of 1.25, comma, minus 1.5 plus the square root of 1.25. On that open interval, we would know that a solution to this differential equation exists. Does that make sense? All right. Well, I think there's a problem or two in your homework. Hopefully that'll help it settle in. That's about all I have to say about these. With that, we turn the page and start our work on the Frobenius method. So what's the Frobenius method about? Like suffering, much suffering. Okay, it's somewhat accurate. But it's actually harmless. Honestly, it is just a natural extension of the power series method. All right. Sometimes Frobenius solutions are just power series solutions. So let's look at it here.
Look, I got it.
Oh, you already got it? All right.
Yeah.
I saw you were checking on something, so I wasn't sure. Thank you. So last time I defined for you guys what a regular singular point was, right? A regular singular point was one for which it's a singular point, all right? So in other words, if we look at P and Q, we got some sort of division by 0 or something bad is happening so that they're not straight analytic, all right? But, nice thing is if P and Q are such that when we multiply by x and we multiply by x squared, those are analytic, then this is said to be a regular singular point. So by the way, I'm going to focus our attention solely on the center being 0. The reason that's reasonable is you can make a substitution x equals to t minus a that will move 0 to a. And so all the formulas in this section can easily be translated to centers other than 0. And so we'll focus on 0 because it reduces the clutter a lot. I'm sure you've experienced that in your homework, right? Do you much prefer to work one that you're trying to find solution centered at 0, right? I think I do. But so let's focus on that. Now, so to say x times p of x and x squared times q of x are analytic, what that means is that, well, in retrospect, it means that the power series, quote unquote power series, for p and q had to look like this. See, if multiplying by p by x gives me something that's analytic, that means that it has a well-defined Taylor series, right? You've got a constant, an x. What on earth happened there? What is that? I don't remember that being there. Oh, no. This should be p2x squared, right? And that's supposed to, oh, good grief. And this is supposed to be p2x, right? I'm not sure what happened here. I feel like I might have went to fix one typo and created another. I think that might have been what happened here. I'm not sure, but anyway, this is supposed to be p2x. This should be p2x squared. The point is, if it's a regular singular point, x times p has a Taylor expansion, right? And x squared times q has a Taylor expansion. So if you divide, yes?
Was it supposed to have the x in front of it too, or?
No. This is supposed to be p2x, p2x squared. It's, yeah. So if these have Taylor expansions, like so, if you divide this by x, you get back to that. It's supposed to be an x. And if you divide this by x squared, you actually get back to this, right? Q naught over x squared, q1 over x plus q2 plus q3, and so forth, all right? Now, these are not Taylor expansions. These are what are known as Laurent series, right? Laurent series, what that means is you have a Taylor series and you add a few reciprocal terms. Finitely many, though, all right? Like a Laurent series can't have infinitely many reciprocal terms. Is no allowed. But what that also means is that there's what's called a pole. And so the pole is said to be removable if you can multiply the function by a sufficiently large power to remove the singularity. So in the language of complex variables, what we're really saying is that P has a simple pole at 0, and Q has a pole of order 2 at 0, right? So of the sorts of singularities you can consider, these are the most sort of well-behaved ones. That's why they're called regular singular points. And so anyway, getting on with it here. This is the theorem. There exists a number r and coefficients a sub n such that when we try to solve y prime prime plus py prime plus qy equal to 0, we can let our solution look like this. That should look kind of familiar. It's pretty much the power series solution. What's the wrinkle? It's a significant wrinkle. Notice that we have n plus r. Our power series solutions have just been an x to the n, right? In some sense, power series solutions, we just set r equals to 0 in this solution template. Now, once you have that, if you're willing to forge ahead into the wild unknown and assume that calculus still works in the same way it did in calculus 2 for these kinds of almost power series, well, then you might assume that differentiation works term by term, right? And in fact, if you were in a serious applied analysis type course, you might prove that. I won't prove that in here, but it's true. You can differentiate term by term. And I bet this is what you guys would have written down if I just, I don't know, put you on a desert island, put you in here, make it worth 50 points. I don't know, whatever makes sense. But certainly, you would have probably figured out that the derivative of this should be that, and the second derivative should be that, right? Notice that I keep n equals 0, because there's no reason that n plus r should be 0 here. Like the base term in this expansion, which is called the Frobenius solution, the base term in the Frobenius solution is a naught x to the r. That doesn't have to differentiate to 0, because r could be anything. Okay, so then what we do is we just take these and we plug them into the differential equation, all right? But what I do is I multiply the differential equation by x squared. Why do I do that? Because doing that makes this analytic, right? And it makes this also analytic, because if xp is analytic, x squared times p is also analytic. Which means that these have Taylor expansions, which we can use to calculate with, right? And so that's what this looks like. We got this. That's my second derivative of my Frobenius solution. Here's, this is xp. There's a leftover x, right? Because remember, xp is analytic. This x squared p, there's a leftover x in addition to, come on, look at that. Still wrong down here. Well, I guess, if nothing, I'm consistent. And I'll probably forget after this lecture. You probably can go back last year and see me making the same annoyed comments to this, where I will invariably forget to go edit these notes after this class. I'm sorry, guys. I should probably apologize to last year while I'm at it. But anyway, this is x squared q times that. If you've been doing any of your homework on power series, you kind of have a sense of where we're going with this. Come on. So hence, we have the following. This is y prime prime term. This is the x squared p y prime term. Again, with my stupid... Anyway, I'll get over it. Anyway, at some point I stop ignoring my errors and say true things anyway, so let's just go on. So plug in the Frobenius solution, we get something close to this. Then the more interesting thing is, if you look and you focus, for this to be 0, what that means is that order by order we have to have vanishing of these solutions, right? So if you look at the lowest order thing, is the coefficient of x to the power r. All right, so x to the power r here is coming from n equals to 0. N equals to 0 picks up, tell you what, since I've got so many errors in here, let's turn on the lights and let me just fuss with it for a minute. All right, so we want to look at x squared y prime prime plus x squared p y prime plus x squared q y equals to 0. And we're given that p, well, xp, right? We're given that xp is equal to what? It's equal to, say, p naught plus p1x plus p2x squared. Right? We're given that x squared q is equal to q naught plus q1x plus q2x squared, right? So notice then, and we're assuming that y is basically equal to a naught x to the power r plus a1 x to the power r plus 1 plus dot 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 dot. I mean, those are the first two terms in the Frobenius solution. That's n equals 0 and n equals 1. So like, let's see here, y prime would be r a naught x to the r minus 1 plus r plus 1 a1 x to the what? X to the r, right? What's y prime prime? R times r minus 1 a sub naught x to the r minus 2 r times r plus 1 a sub 1 x to the r minus 1. Right, so there's your y prime prime. Let's see here. I should probably also write out what's x squared times p then. It would be x p naught, right? Plus, I'm sorry, p naught x rather, plus p1 x squared, and so forth. So I think I have everything on the board to think about what is coming from this right here if we just look at the lowest order terms, right? So let's see here. X squared y prime prime contributes what? And x squared p y prime contributes what? And how about x squared q y? What does this contribute? And here I'm talking about, it's totally ambiguous what I'm asking at the moment, but I want to say to the x to the r term. That's the lowest order thing. See, because you notice x squared times y prime prime, what happens? X squared times y prime prime. So we have r times r minus 1 a sub naught x to the r plus higher order stuff. So that's the lowest order term in the x squared y prime prime. So it contributes r times r minus 1 a sub naught. How about the x squared p term? Well, it's x squared py prime, actually, right? What's y prime have in it? It's right here, right? Yeah, so we're thinking about we're thinking about multiplying this thing, right, with this thing. That gives me what goes here. If I look, what's the lowest order thing when we multiply those? Yeah, it gives us x to the r when we multiply this times that, right? And it gives us a p0, a0, r. Do you see that?
Is there a reason why you switch the order?
No, these are just numbers. Yeah. And then how about x squared q? X squared qy. So the lowest thing is q naught. What's the lowest thing in y? A naught. So we get plus a naught q naught. So in total, we have the following. We have a sub 0, r times r minus 1, plus p0 a0 r, plus a0 q0. This is all from the x to the power r code. This is the lowest term in the Frobenius solution. This must be 0 to have the Frobenius solution work. So that gives you two choices, right? I mean, there's an a sub naught we can pull out, right? So we pull out a sub naught. And it turns out, definition, the indicial equation, is r times r minus 1 plus p naught r plus q naught equals to 0. Solutions are called exponents, I think, if I remember right, of the Frobenius solution. So there it is. Despite my many typos leading up to this, I did find r times r minus 1 plus r p naught plus q naught, just like we found together just now. I just want you to understand it's nothing that profound. It's just plugging in the Frobenius solution and going order by order carefully. Okay? You can hit the lights again. So, if I can find my laser. Oh, there it is. So, I mean, this would be, and I don't know what follows here. It's like, yay, I mean, that's true. I don't know how useful it is. I don't really do anything with these, but just for giggles, here's the next thing up. This would be the coefficient of x to the r plus 1. And here's the coefficient of x to the r plus 2. You see these equations start intertwingling, like a sub 1 and a sub naught, and a sub 2 and a sub 1, and they're all going to get all wrapped together, as you go on. But I think it's good for us to look at an example at this point. So let's solve 3x y prime prime plus y prime minus y equals to 0. At x equals 0. x0 is a regular singular point. If I was to, if you divide this by x squared, what do you get? I'm sorry, King. Thanks. We've got 3x y prime prime, right? 3x y prime prime divide by x squared to get it to our standard form. Excuse me, divide by 3x, right? So we got y prime prime plus 1 over 3x y prime minus 1 over 3x y equals to 0, right? So this is my p, this is my q. What's x times p? What's x squared times q? Are those analytic? See, x times p here is just 1/3, right? And x squared times q is, looks like minus 1/3 x. So yeah, these are analytic. They're kind of boring in that regard. What's p naught, what's q naught for this example? Before I go on to my notes. So this means that p naught is actually equal to 1/3. And this actually means that q naught is equal to 0. There is no constant term in the power series for minus 1/3 x. So the 0th term is just 0. So when I go to calculate the indicial equation here, the q doesn't figure into it. Just the p. Okay. You can hit the lights again. Sorry. Anyway, so here's my y. By the way, we can re-index this sum to be sum n equals 1 to infinity of a sub n minus 1 x to the n plus r minus 1. Do you guys agree that these are equal? Where does this one start? It starts at a sub naught x to the what? X to the r. Where does this one start? A sub naught x to the power r. So if you could start, I mean, you can make an explicit substitution and see that those are in fact equal. I just re-index the sum. Here's your y prime. Looks like this, right? And here's 3x y prime prime. So in principle, y prime prime would have x to the n plus r minus 2. But because I multiplied by x, it makes it x to the n plus r minus 1. Why did I do these calculations? I mean, why did I re-index this one? It's pretty simple. Because if I do that, then this one and that one and that one, they all have the same expression, right? So I can add these sums. Matching the structure here. Come on. Therefore, 3x y prime prime plus y prime minus y yields this. Yeah. So here's the 0th. I peeled off the 0th term to emphasize this is the indicial I guess it's the indicial polynomial. I don't know which one to call it, but so we need two things. We need that this vanishes for every n greater than 1, and we need that this is equal to 0. So that suggests that we should choose r such that this quadratic equation in r is 0. And then if you put this equal to 0, you can solve for a sub n in terms of a sub n minus 1. This gives us a wonderful sort of recursive tool to build new coefficients from old, all right? Just like with the power series. So this one, if you factor it, we either get exponents of 2/3 or 0, all right? I plug in 2/3 now into the star. Plugging 2/3 into the star equation gives me this list of recurrence relations. So what I'm doing is here's the lowest one. A sub 2 involves a sub 1, but a sub 1 involves a sub naught. So I take the first equation and pop it into the second, right? Then at the third, that relates to 3 to 2, but 2 is related to the 0th one, so I plug this into there to get that, and so it goes. You do enough of it, and the pattern eventually hits you over the head, and you go, okay, well, that's about as good as I can do here. A sub n is a sub naught over 5 times 11 times 11 times 14, 3n plus 2 times n factorial. See, what I did was I pulled out the, what I do. You notice I've got a 3, 2 for a sub 3. For a sub 2, I've got a 2 times 1. It's there, 1. And a sub 1 is a 1 factorial right there. A sub 4, you can see there's a 4 times 3 times 2. That's a 4 factorial. So this pattern continues, and you're always getting this string of numbers that are 5 times 8. So I turned this list around to 5 times 8 times 11 times 14. It goes all the way up until the top number, 14, which is what? This 14, as it relates to 4, is the same as this 11 relates to the 3, right? And if you look at that, that's actually just going to give you 3n plus 2. You can check it out. 3 times 3 is 9 plus 2 is 11. 3 times 4 is 12 plus 2 is 14. Right. Anyway, the Frobenius solution for exponent 2/3 is this guy. Is that a power series? It is not. Notice the 2/3. This is not a power function, right? Well, I guess it is a power function, but we don't call it power series. For power series, we insist that we're adding together monomials, like x to some integer power, positive integer power. Then you've got one other exponent to go, right? N equals to 0, R2 equal to 0. In this case, the star equation reduces to this. And then again, I attack it order by order, looking to shove the lower order into the higher order until I systematically can see some pattern if I can. You don't always see a pattern, but if you could see a pattern, you'll try to look for it. And this one happens to be this, which gives me that solution. And so there you go. This is the Frobenius, the general solution to this problem by the method of Frobenius. It's really not much different than your power series solutions, right? What's the extra wrinkle? The exponents, right? This little r. Here's another example. X squared y prime prime plus 3x y prime plus y equals to 0. If we divide this by x squared, we can see that p is 3 over x and q is 1 over x squared. So this one has p sub naught equals to 3 and it has q sub naught equals to 1 actually. All right. And like I said, p sub naught is 3, q sub naught is 1. The indicial equation is this guy, which is that guy, which is r plus 1 squared equal to, so we have both of our exponents are minus 1. So I plug that in to the Frobenius template, and it gives me this. In fact, we find this, which provides that n minus 1 times n minus 2 plus 3 times n minus 1 plus 1 times a sub n is equal to 0 for n equal to 0 to whatever. What happens if you put n equals to 0? Put n equals to 0, I get, looks like I get 2. 2 minus 3 is minus 1 plus 1 is 0, right? So n equals to 0, I get 0 times a sub 0, which tells me there's no restriction on a sub 0. That's what it says. Okay, so a sub 0 is free. No condition for a sub naught. In contrast, if you put n greater than or equal to 1, this gives you a non-zero number times a sub n is 0, which forces a sub n to be 0 for n greater than or equal to 1. So the whole Frobenius solution, it all dies except for the 0th term. It truncates it at that order. And this is really not surprising. So the Frobenius minus 1 exponent x solution is just a naught x to the minus 1. But you guys may recall, we studied the Cauchy-Euler problem before, right? This is a Cauchy-Euler problem with repeated roots. So we know, not surprisingly, that the solution is c1 times 1 over x. That's the Frobenius solution we found. And then we know from our previous work that the next one is log x over x. Right? We do log x times the first solution to get the second in the case of repeated root for the Frobenius, for the Cauchy-Euler problem. This also kind of warns you, there's something missing from our current story, isn't there? Right? If we have a repeated index, what do you do? It's a question. Our next example. What if your indicial equation ends up giving you complex roots? This example shows you what to do there. So x squared y prime prime plus xy prime plus 4 minus x times y equal to 0. X not equal to 0 is regular singular point. You can see that because my p would actually be 1 over x, my q would actually be 4 over x squared minus 1 over x. So q naught here would be 4, and p naught would be 1, as you can see down here. So this gives me the indicial equation of r squared plus 4. So in this case, my exponents are plus or minus 2i. Now, otherwise, what's all these calculations? What am I doing here? Otherwise, what's going on here? So what I'm doing is I'm just plugging in the Frobenius solution, which is an x to the n plus r, and I'm multiplying 4 minus x times it, right? So when I multiply 4 minus x times y, I get 4 times the Frobenius solution, right? And then over here, notice the plus 1, because it's x times the Frobenius. So otherwise, the same, but you get a minus. And so that gives me these two things. N equals 0 to infinity, j equals 1 to infinity. The reason I did that was so that these would look similar. I wanted to reindex them so I could add them. You notice the cost of that is that now they have different starting points. So I started 0, 0. Now I go from 0 and I start at 1. But that's for the best, because later I'll be able to combine these, because now they have the same type of exponent in the x, right? I have to do that reindexing in order to add things. Then I'm working on xy prime. Xy prime is a sub n plus r. This would be x to the n plus r minus 1, but I multiplied by x, which brought it back up to n plus r. I like this one because it matches what I've already got. X squared y prime prime is going to be this. Again, this would be n plus r minus 2, except since I multiplied by x squared, it brings it up to xn plus r. But this is good. All of this guy, that guy, and the two things that come from this, I now have them all in the same format, so I can add them appropriately. And that's where I get this step from. You notice that 0 is an oddball, right? 0 is an exceptional thing, because I got this one starting at 1, and these two guys start at 0. So this one, and that one contribute their 0th term into making up the indicial piece. And then we just keep n equals 1, j equals 1, n equals 1, n equals 1 to infinity for these other terms over here. If you've taken the time to do power series carefully, like I did last class, this is just the next logical step. It's ugly, I understand. I don't dispute that. I lost a week of my summer once to this thing. When I was learning this, there was this point where it took me 2 days to solve one of these stupid things, because I was laboring under a certain misconception, which I will not tell you, for I do not want to wrap you into that. Anyway, so here it is, and then you've got a relation between an and an minus 1. So you solve for an in terms of an minus 1, and you get this. And then we're off to the races, because we know that r is equal to plus or minus 2i, and I can put that into there to derive the relation between, a sub the different a's. Now, since r is complex, it pays off to do a little bit more work with the star equation, just to keep it real, so to speak. So when I plug in r equals to 2i, I get this, right? And that is just going to make a horrible mess if I don't fix it before I start iterating. Because I want answers that are in Cartesian form. Eventually I want stuff in the form a plus ib, right? So a plus ib in, a plus ib out. 1 over a plus ib in, 1 over a plus ib out. You don't want 1 over a plus ib upon 1 over a plus ib. This is bad. You want to... So I take the time to put this into Cartesian form at the start. All right? Which isn't a big deal. I just multiply by the conjugate of the denominator over the conjugate of the denominator. Standard technique, right? Anyway, that gives me n squared times n squared plus 16. I mean, in its sort of, what's the word? Primitive form, it would give us n to the fourth plus 16n squared, but I just factored out an n squared. Because it pays to simplify the recurrence relation before you start plugging numbers into it, right? If I can make a simplification at the level of algebra for all n, that means I'm not doing it every step of the arithmetic, right? So it's so important to cancel things if they can be canceled at this stage. Because if you don't, then you're inviting yourself to dozens upon dozens of cancellations eventually. I mean, it just, anyway, enough. So there I go. I've got my star squared, which is, sounds like some kind of transformer maybe, I don't know. But so a sub 1 is a sub naught times 1 minus 4i over 17. Yay. A sub 2 would be a sub 1 times 4 minus 8i over 4 times 4 plus 16, which would give me this. Multiplying it out, which would give me a sub naught 28 plus 12i over 17 times 80. All right? By the way, this is not in the book. So, put it all together, I find the following complex solution to my problem. A sub naught x to the power 2i, that's my a sub naught x to the r term. And then here's my n equals 1, which we found was minus 1 minus 4i over 17, x to the 1 plus 2i. Then we've got our 28 plus 12i over 17 times 80, x to the 2 plus 2i, right? And then what do? I go ahead and separate this into two pieces. The real part of the series, a of x, plus I times the imaginary part of the series, b of x. See how I'm doing that? There's not much going on there really, except that this gives me an x squared times x to the 2i. This gives me a x times x to the 2i. So I'm just factoring the x to the 2i out front. And I'm going ahead and keeping the 1/17 and the 2 over 17 times 80 together as the real piece. And I'm taking the I pieces out. So take the I out, which is really cool if you're a sand ninja. But let's see here, minus 14 over 7x, 12 over 17 times 80 x squared. You see where they're coming? I hope you see what's going on here. It's awful, but it's straightforward. So great, this is a complex solution. Now, x to the 2i, we talked about this back when we talked about the Cauchy-Euler problem, remember? X to the 2i should be understood as cosine 2 log x plus I sine 2 log x, all right? So, what this gives you then is y equals a naught cosine 2 log x, a of x, minus sine 2 log x, b of x. This is the real part of this above solution. And then, likewise, the imaginary part of the solution is a naught sine 2 log x, a of x, plus cosine 2 log x, b of x. Again, this is a complex solution. As usual, the general real solution is found from adding together the real and imaginary parts of the general complex solution. So I just peel off the I and keep the thing, and there you go. This is the general complex Frobenius solution, of which I've only made explicit the terms up to order x squared, right? Well, times cosines and sines of logarithms. This is definitely not something that was in our toolkit from before, right? We did not have solutions like this in the previous arc of the course. This example is not especially exciting. I think I'm going to skip it. Just end here with the repeated root. I'm going to talk to you about the repeated root technique briefly. So we talked about this before. If we take e to the rx, right, in the start of the course,